Today we are going to talk about the quantum cryptography and the secure communications. So I'm Shanika. So my team members Devashish and Swati will also share their knowledge with you today. So and we today we start with the most basic things. Yesterday you got all the you got basic quantum fundamentals, very clear presentation and very clear knowledge distribution there yesterday. So, but for the main reason for this quantum secure communication, we will start with the most basic quantum idea. The classical bit can only be 0 and 1, nothing in between. So, but a qubit, however, behave differently. So the main thing you need to understand clearly is that qubit has two basic states, but infinitely many possible combinations. The two basic states are ket0 and ket1. These are like the two axes or reference directions for the qubit states. The general qubit is ket5 equal alpha ket, like in this way, alpha ket1. These are like the two axes or reference direction. So, this equation. So alpha and beta here is like complex numbers. So infinitely many alpha and beta pairs satisfy the equation. It is just like infinitely many points lie on this pair. So if we take a real intuition here, suppose a painter has only blue and yellow basic colors, but can create infinitely many shades of green by mixing them in different proportions. Similarly, a qubit has only ket0 and ket1, but can form infinitely many superpositions by choosing different values of alpha and beta. So then the superposition is the foundation of all quantum advantages and quantum security. Today we are going to take the practical example on that. So here it takes we say, sorry, that's independent versus entanglement qubit. You know that now we go beyond the single qubit, right? Two qubits can behave independently, but they can also be entangled. If you have two qubits that are not entangled, each one acts on its own. So whatever happens to one doesn't affect the other. Their measurement results are uncorrelated, but if the two qubits are entangled, they behave like one connected system. That means if you measure one, you immediately know the state of the other, even if they are far apart. Okay. So for example, then you always get matching results like both 0 or both 1, or always opposite results, 1 0 or 1 1. So that's why entanglement is sometimes called like quantum connection or the invisible link. But this is not communication. Exactly, no information is sent here. It is simply shared quantum state. When two qubits are maximally entangled, they form one of the four Bell states you can see here, and they are special, perfectly correlated states that form an orthonormal basis of two qubit spaces. So they look like similar. You can see in here that the diagram shows, but yeah, they look like similar, but differ by which basis states they connect. Right? So for example, you can see 0 0 1 1 here and 1 0 and 0 1 and 1 0 here, and whether the connection is positive or negative. You can see how these Bell states are generated. This relative basis is given what gives each Bell state its identity based on these notations and the states. So okay, uh, before move on to that, I want to make sure that you all are not confusing with these notations. For example, the two digits inside the ket here represent the states of two different qubits. The first digit is the first qubit and the second digit is the second qubit. Okay, so that means in here, first qubit is in a state 0 and the second qubit is also in the state 0. And another one important thing here is this state is also known as an EPR pair. I think you heard that. EPR pair. We created this EPR pair using only two gates like Hadamard and CNOT, which we next talk about in the entanglement part. This is the fundamental building block of many quantum technologies like teleportation, quantum key distribution, and quantum network, and also secure communication in quantum. So, what we are going to explore today. So, here is another word, orthogonality. It's like a fancy word, but simple idea there just means that each bell state is completely different from the others, and you can tell them apart with measurement. That means it's like a different musical notes. Suppose that this is intuition, so the musical notes they don't overlap or sound the same sometimes. So then this combination is like so they form a basis, meaning any two qubit state can be built from combination of these four, right? So just like any color can be mixed from red, blue, and green. So but here, as I explained earlier, that how we get these four kind of Bell states, and these things are related to the entanglement and teleportation. That's why I explain in quickly. So, and the next thing that you need to know here is now you may have a clue between like some people think if the qubits are connected, as I mentioned, can I send a message instantly? Absolutely no. That's what the no signal in role means. It because even though the results match, each individual measurement is random. Alice and Bob only see the correlation after they talk using classical communication, which still travels at or below the speed of light. That means the entanglement gives shared randomness, but not actually instant messaging. That means it's it's give the security. So that's very important to understand here. So and the next thing is no cloning theorem that you can see here that it is a special quantum mechanic called no cloning theorem here, which we use in the entanglement and teleportation. In normal computers we can copy bits like 0 into 0 0 and 1 and into 1 1. So but in quantum system, you cannot copy an unknown quantum state. Why is that? Because copying would require knowing exactly what the state is, but measuring it changes it in here quantum. So if you try to clone it, you destroy the original information. So think of it's like trying to take a perfect mode of a soap bubble, but moment you touch it, it pops. Like the similarly, it's happening in the quantum. This rule is very important for the quantum security. It means no one can secretly copy your quantum message, and we say this as the no cloning theorem. So this is what exactly we want to know about the fundamentals for the when we talk about the entanglement. So the next thing that we should understand here is this entanglement. Here, I'm going to explain mainly two things. What the state 00 means and how Qiskit represents it and what happens when you apply Hadamard gate only the first qubit and so on, things which are related to entanglement. So in here I mentioned here this is the first state that we are going to entanglement. This is the state that we got after we apply the Hadamard gate on the qubit 0 here. You can see I will explain all these things in demonstrations. Don't worry if you don't understand here. And then we just to get create the entanglement, we use you mute all. Okay. So this is the starting point of entanglement, and you can see here what gates that we are going to use here. Hadamard gate, H gate, and CNOT gate. So this is like you to understand what these gates do. I will not going to explain here those things in much details because I'm going to demo those things. Yeah. So this is what the simple entanglement block, and then in here I'm going to show you what the state 00 look likes and how it's represent here, and what happens when you apply Hadamard gate into onto the this first qubit. So this creates two qubit system. No gates applied here. So the quantum state is get 00. This is get 00. So which means Q0 is also 0 and Q1 is also 0. Then the printed amplitude, you can see here, it's correspond to the amplitudes of basis states. You can see there's 100% is in 0, 0 and nothing else, because this is exactly what we expect because we haven't touched the qubit yet. Then you may think here is a question for you to think like what a classical bit string does this corresponding to? And you may think what I I think you all know this is 0, 0 because both qubit would measure 0. Okay, now we apply the Hadamard gate only to qubit 0. When we applied Hadamard gate to qubit 0, it goes into superposition into ket 0 and ket 1. This is after applying Hadamard gate. So this is the superposition of first qubit only. So then the second qubit stay ket 0 still, and then combined state or the full qubit circuit becomes superposition of ket 0, 0 and ket 1, 0 given this equation. Okay, so which two basis states are now populated is here. This is the answer here. And why is qubit 1 is still 0? Because this is qubit 1, qubit 1, this one is still 0 because we didn't put it Hadamard gate or anything to it. This we didn't touch it yet. So next, what we are going to do here is we just wanted to go to the next step of creating the entanglement circuit. So now we come to the second half. This is creating entanglement pair, the next half. So after preparing the superposition, we now apply C naught to build in the Bell state. So this is it. So we start with the superposition of, that 0, 0. In here, you can see I just explain all the things one by one, and we start with the superposition 0, 0 and 1, 0. When we apply C naught with Q naught as control, right? We get this C control as is Q naught, and the target is Q1. This is the C naught gate, yeah. So it's now that the 0, 0 stays the same, but 1, 0 becomes 1, 1 because the second qubit, you can see here, 0, 0, no control, no flip in here, it just same similar, but in here flip second qubit. So the final state becomes in this way. After we put the C naught, we got this one, it's the Bell state. So this means the qubit are now entangled, right? They always match. That's why we only observe 0, 0 and 1, 1, and we never get 0, 1 and 1, 0. Okay, now you may think why are outcomes 0, 1 and also 1, 0 absent there? Why outcomes not containing 0, 1 and 1, 0? So I would say that the quantum measurements can, sorry about that. Quantum measurements can only produce outcomes that have non-zero amplitudes. What it says. Because neither 0, 1 or no 1, 0 ever appear in the final wave function. You can see here that resulted state vector here. You can see this resulted state vector. Explicitly shows that amplitude 0, 1 and 1, 0 is 0. Can you see now results here? So quantum measurement can only produce outcomes that have non-zero amplitude. So you will never measure 0, 1 and 1, 0. That's why it doesn't contain those two states here. So this is the signature of entanglement. So the outcome are perfectly correlated. So, and the other thing that you may think, what is this J? If you have any clue in confusion in that, I would say that uh, let me explain this quickly. Like in Qiskit, quantum amplitudes are written as a complex numbers like this. Amplitude is A plus Bj. So J is the imaginary unit, and these here J is the imaginary unit, and the 0.701 is the real part. And since the imaginary part is 0, so this is just means 0.701. No panic right here. Okay, so because we got this here in Qiskit, Qiskit shows the imaginary part even when it is 0, because quantum amplitudes are always complex numbers in general. So that's why it's this kind of results you're getting. So, and next thing is that now we already created the entanglement state and now know how to create the entanglement, which is the basic for the teleportation. So now we come to the main part. This is the main part of the secret communication. So in this diagram, you can see Alice has an unknown qubit. So she and the Bob share an entangled pair. Alice performs a Bell state measurement that destroys her qubit and produces two classical bits. She sends those two bits to the Bob. Bob uses them to apply correction to his half of entanglement pair. This after this correction, Bob's qubit becomes the exact state Alice originally had here. This is called the quantum teleportation. In quantum teleportation, does not move a qubit from Alice to Bob. Instead, entanglement plus measurement, two classical bits allow Bob to recreate the exact quantum state that Alice had. So the at the measurement, Alice's original state will be disappears and Bob's qubit becomes a new copy of that. So this is actually satisfy the no cloning theorem and no faster than light communication, and also this is perfectly secure transfer. So now let's yeah. In here now let's walk through the full teleportation protocol using actual quantum gates. After that, I will show you how the demonstration of this teleportation. So we quickly go through these steps, and here we go through it in 5 steps, moving from preparing an unknown state to Bob recovering it. So step 1, Alice prepares a qubit in a general state using rotations. In the example here, we use the RY and RZ. So Alice prepares a qubit in the state psi, which is defined as Ry of phi over 3 followed by Rz of phi over 5 applied to the state this qubit 0. So this results in a general superposition alpha times that the equation alpha time ket 0 and plus beta times ket 1. So this is Alice's unknown quantum state. The one she wants to teleport. This is the one she wants to teleport. She cannot copy it or measure it, so she must teleport it. So in the step 2, you can see here that the circuit diagram is having this two part that we create here barrier. This is just a this is just to show the separation. Alice and Bob share the entangled pair between Q1 and Q2. Here apply the Hadamard gate to the Q1 and the C naught from the Q1 and to the Q2. This creates the Bell state. So you know these steps, how we create the EPR or the entanglement previously. So then Alice keeps Q1 and the Bob has Q2. So this entangled pair is the quantum resource that makes teleportation possible. So now Alice now performed the Bell state measurement on her unknown state Q0 and her entangled qubit Q1. This involves T naught from Q naught to Q1, Hadamard gate on Q naught. So measuring Q naught and Q1 in the computational basis, it gives you the measurement produces two classical bits here because it produces two classical bits which we need to send to the Bob. So Alice measurement destroys her qubit and entangles the measurement outcomes with Bob's qubit. These two classical bits determine how Bob must correct his qubit, which is that entangled bit. So then in the step 4, Alice sends her two classical bits to Bob through the classical channel. Bob then applies corrections to Q2. You know that these corrections has Z and X and those are quantum mathematical things. So these corrections undo the scrambling created by Alice measurement. So here, these measurements. So once Bob applies the right corrections based on these conditions, that his qubit becomes exactly what that the unknown state that the Alice sent. So now the step 5 is now Bob has the final qubit. He can choose a measurement basis So that means these two shows that measurement basis as Z basis and X basis. So normally the Z basis measure the computational state and X basis measure check the phase on coherence. So Bob now hold the qubit that contains a state, and also Alice's original qubit no longer exists. The state has been teleported now. The Alice original qubit has no, it's destroyed, and now along the teleportation process that the Bob receives the measurement. So then this is just a simple example. So the how we created practically these quantum circuits. I will explore. I will show you the um, demonstration here. I think it will help you to see how it's going on. So okay, side by side, I will show you this one. It will be better. Yeah, I hope you can see it now. Yeah, this is the teleportation process, step-by-step process that I explain here. You can see how we code here. Here I use this Visual Studio Code, whatever that the environment that you can use here. But in here I have already used the virtual environment, and you can, I don't need to include these things installations, but if you are working on this general platform that you need to install these things to work on the quiz kit. So here the first thing that I'm doing here is imported and also cleared the helpers here to create this teleportation. So now let's see how this practical implementation happened. Okay, the first we import the Qiskit classes. We need to build circuit and the AR simulator and all what we need to run them. We also need NumPy to get numerical constants like phi and to do some simple maths here. So we define a small helper function which is called prepare psi here. So because it's for this given circuit like qubit index, and this is qubit index like, and angle theta and phi, it applies the r by rotation and by theta, and here r is at rotation by phi on that qubit, which is I explained here. So mathematically this prepares the general qubit state, which is given in comment here as I show you here. So for the demo we chose here these two concrete angles here, theta 5/3 and phi is 5/5. So that means our test state is genuine superposition of ket0 and ket1 with both amplitude and phase. You mean this gives the teleportation something non-trivial to do, but just not just send in a plain ket0 ket1. I think you understand what I mean, that because uh, if I explain it, if Alice prepared just cat 0 and cat 1, teleportation would be trivial. That means Bob would always get the same basis state. By preparing a real superposition with rotation gauge like this, we give the teleportation protocol something meaningful to transfer both amplitude and phase. Okay, so now then before going to the next step, yeah, this is here for the evaluation, but I wanted to show you that how these two matching after we teleport to the Bob. That's why I get this reference measurement. What is the exactly the Alice measure? So Alice wanted to send, right? So let me show you this one by running. It's just, yeah. Here, Alice reference measurements, he got this kind of uh, measurement here, one and for the 1 and the 0. At the end I will explain what it is and how it's going to be connected with the Bob's result. So as the step 1, this is the step 1, this is the state preparation. We first create the 3 qubits in the quantum register. This is called Q. So in here you can see a qubit 0 will hold the unknown state of psi, and qubit 1 is Alice's EPR qubit, and qubit 2 here is Bob's EPR qubit, in similar to this one. So next we create a classical register. So it is for the is for the store measurement outcomes. Okay, so for example, CA has 2 bits for the Alice Bell measurement results, and CB has 1 bit for the Bob's final result. So final readout. So we now build a circuit called this QCTEL. Now that uses these 3 qubits and both classical registers. So this circuit represents step 1 teleportation, preparing the step psi on qubit 0. We uh, call here prepare psi, which applies the rotation gates to qubit 0 with angle theta and phi. As I explained, we need to do this in a non-trivial way. So after this line, let me, yeah, it's running. So we call after this line qubit 0. This is just to show you that what is the draw this circuit. So after this line, qubit 0 is the general state psi that we want to teleport, right? So finally we draw this circuit, and this is the diagram to show you, and then this is just to see that what the allies want to teleport. This is the next part. This is the second step. So, and as here, okay, so now we insert the barriers here just to show clearly separate. This is not the part of this circuit, but in a step 1 we prepare the unknown state on Q0. From then step 2, create the entangled pair between Q1 and Q2. Why we use this barrier is to just to make this circuit easier to read. So now here you can see here this step. So in here we start building EPR pair, or else we can say it's we apply for the Hadamard gate qubit to the qubit 1, putting it into the equal superposition of 0 and 1. I explain all the things in entanglement part. So next thing is we apply the C naught with qubit 1 as control and qubit 2 as a gate here. So because qubit 1 is in the superposition, the C naught here C naught creates an entangled pair between Q1 and Q2 in the best state. So this is our EPR pair. Alice holds Q1 and Bob holds Q2. Now this is the next part that we got here, and yeah, now we created the this Bell state. So now we established the entanglement. The next thing is here. The next step 3 here is um, here also we added this. Here also we added this a barrier here because to show you the separation. And this is the first part of the Bell measurement. So this C naught mixes the unknown state. C naught mixes the unknown state psi with Alice's EPR qubit. If the first qubit 0, nothing happens. But if it is 1, the second qubit will qubit flips. This this step, I think you can understand these things because I explained earlier as well. If it is 1, the second qubit flips. This step begins to convert the pair, right? That the Q0 and Q1 into one of the 4 Bell states, as I explained at the second slide. So this is the second. Then the second part is this and the Bell measurement. So the Hadamard rotates the this is the second part. The Hadamard rotates the message qubit in the superposition basis. So now when we measure, we are effectively checking which Bell state the 2 qubits are in, right? So this is where teleportation needs 2 classical bits. There are 4 Bell states, so we need 2 bits to identify which one Alice measured. So after these 2 gates, measuring qubit 0 and the measuring qubit 1 will tell Alice which of the 4 Bell states she has, and she will send those 2 classical bits to Bob. What we exactly do here, these 2 examples. So I think I have run already this one, and then this one here also. If you want to see this diagram here, I can show you this diagram. Okay, this is too much because I because I need to start the you need to carefully that run this one, because I just having the flow of this, or sometimes it's, if we try running its things, that the circuit will show that how its measurement that it's repeatedly. So these are the two specific figures that you need to know, right? So not the repeated things here. So then we did the second part of the bell measurement here. We know that how to that the Alice send these classical bits, and then how this Bob take these two classical bits to recover that the his received state. So then the step 4 here is classical wires to Bob. That what that means. So in here, Bob's qubit already contained the Scrabble version of Alice's state. In here, I think I can show you. In here, this one. In here, this one, he knows that the classical one. Sorry, this one, he already has this one, and now he has classical channel as well. So now Alice classical bit tell him how to unscramble it. So Alice measures her two qubits and gets M1 and M0 and M1 here. That's why we want to this have these measurements. So she sent those two qubits to Bob, and as I mentioned earlier, Bob checks them, and if M1 is, this is the condition corrections, if the M1 is 1, he applies X gate, and if M0 is 1, he applies Z gate. These corrections recover the exact state psi on Bob's qubit. So uh, Alice, then all the measurements happen, then the Alice qubit is gone, and Bob now holds the original state. This is what we call the quantum teleportation. So in here, to show you what exactly happened in here, that I wanted to get the measurements. I explained earlier that we all um, save these things in the classical registers, and we can take these registers, we can print those in the memories using. This is for you to understand. We run this teleportation circuit here. So this is the example, the Bob's measurement after teleportation. We got these things. This is just to show you the memory. So once that the results got, so you can see here that's how this Alice sends M1 and M2 the measurements, and Bob receives how these measurements happen, and also how these conditions apply on based on these received states. After that, I wanted to show you whether what is this? I wanted to show you here Bob's marginal counts and how these two are correlated. And the Alice, as you can remember, I think you can remember, this is the example of, no, this is the example. Okay, here I wanted to get this exact number here. What we get here? Okay, I wanted to get this one. This is what we get here. And let me check it with the, and here this one. You wanted to, yeah. So once you got this, you get this one, and these are the correlations. Okay. Now we got this values, so you can have, okay, you can see that the Alice measured directly in this way. These are just to, you know that the I explained the alpha and the beta values, which are we get in the distributions, is probability distributions of these states. That this is how we explain that one. How I get this to show you. These are how the counts that they get. This is for the Alice one. This is for the Bob's one. So as you see that the final alpha and beta values are not actually very similar, but it's looks like similar, because you know that the in real time real time, we do have the quantum noise. So this is later you can use it as the fidelity, teleportation fidelity. So okay, this is I will make you available these all these codes, and then you can use it the corresponding these details into your tasks as well. So and quickly, if we go for the next one slide, it's just to show you the very important another communication quantum theory here, the superdense coding. So the superdense coding is a beautiful example of how entanglement makes communication more powerful, because I would say that normally if I want to send two classical bits to someone, I need to actually send two bits, but with superdense coding, I don't need such amount, because if Alice and Bob already share an entangled pair. Alice can encode two classical bits of information by performing a quantum operation on just one qubit and then sending only that qubit to the Bob, right? When Bob received that one, he performed the Bell measurement on the two qubits. So he now holds then because then the measurement outcomes tells him exactly which two bits message Alice encoded here, because I think you understand here if I say it's in simple terms, like how we can say that. Yeah, let's say that teleportation uses classical bits to send a quantum state, and the superdense coding simply does the opposite, right? Using the qubit, using a qubit to send the two classical bits. I think now you can understand what it is. This I gave it this here as well to go for you to understand what actually happened here. So it's like a yeah, actually the key idea is that entanglement boosts the communication capacity, okay, allowing one qubit to carry more classical information than would normally be possible, right? So in I have a simple code for you to show you that, and here also it is not the huge thing here. Yeah, in here you can see this how this super dense coding happen, that you can just to see whatever the things that didn't happen here. So in here when quiz you see here this value. So in the super dense coding, this target message is this, and decoded I put this decoded counts because in Quizgate, this is actually what we got, but I decoded this for you to show you, for the show you this one, because when Quizgate prints measurement results, it shows the classical bits in reverse order. So uh, it is compared to how we logically think of the message. Okay, so even though the real decoded bits are 1 0, Qiskit prints them as a 0 1 because it writes the bits as C1 and C0 instead of C0 and C1. So when we reverse this bit string back to the logical order, we get this correct message 1 0. So nothing is wrong with our circuit. It's just Qiskit's bit order convention, right? So that's why we get in this one, and then we need to decode it inside. Okay, this is how this super escort is simply working. Then this is just for the one qubit that I show you. But if you have one message, that if you wanted to say these all these messages, so you can see what happens here. You can see this what happens here. This you mean you send these different messages and these accuracies happen here. Then you get these kind of measurement distributions. So this is quick overview of the superdense coding as well. Here, this you can simply understand this one if you thoroughly understand the teleportation and entanglement. I know. So okay, this is for the end of this teleportation part. If you have any question, you can ask at the end of this session, and also tomorrow onwards, you can ask anything related to these things from discussion forum as well. Now, I think that Devashish will continue for the other parts of very special part for the cryptography and the quantum cryptography. So I'll stop sharing and hand over to the Devashish.
Thank you. Just a second. Is it visible?
Yeah, yeah.
Yes. So, hi everyone. I'm Devashish, and today I'll start by talking about what key distribution is and why it matters, and why quantum communication offers a new approach to securing it. So, whenever two parties want to communicate securely, whether it's your phone talking to a bank website or two servers sharing data, they need a secret key. This key is essentially a special piece of information that lets them lock and unlock messages. The process of getting this key from one person to the other is called key distribution. In the classical world, most of our security depends on mathematical problems that are extremely difficult for today's computers to solve. A well-known example is RSA encryption, which relies on how hard it is to factor large numbers. To understand how this works, we can look at the illustration on the right. So if Alice wants to send a message to Bob, the first thing Bob does is generate two keys, a public key and a private key. Bob sends the public key to Alice, and anyone listening can intercept it, but it doesn't matter. Alice uses this public key to encrypt her message and then sends it to Bob. When Bob receives it, only he can decrypt it because he has the private key that never leaves his possession. So, this system has protected global communication for decades. However, it has a major potential weakness. So, in 1994, mathematician Peter Shor discovered what we now call as Shor's algorithm, a quantum algorithm that can factor large numbers exponentially faster than any classical algorithm known today. So, when we get a large scale quantum computer that has very low noise and errors, Shor's algorithm could factor numbers that would take classical computers centuries or even longer. This means RSA and many other classical encryption systems would become breakable. So, even though we don't yet have perfect error-free quantum computers, the theoretical possibility is enough to raise concern. If powerful quantum computers arrive, an attacker could use Shor's algorithm to recover private keys from intercepted public keys, and the entire classical encryption system could collapse almost instantly. Because of this, researchers have started looking for alternatives that do not rely on mathematical difficulty, and that brings us to quantum communication. So, quantum key distribution, which is also called QKD, uses the laws of physics, specifically quantum mechanics, to distribute keys securely. Unlike classical methods, the security here doesn't come from a hard math problem. It comes from the fundamental properties of quantum particles. For example, when you measure a quantum state, you inevitably disturb it. This means that if an eavesdropper tries to intercept the key, Alice and Bob can detect it immediately without the quantum signals will look different. So, quantum communication offers something extremely powerful, physics based security, which remains safe even against future quantum computers. Now that we have talked about why quantum communication is important, let's look at a simple comparison between classical communication and quantum communication. So, as we know, classical systems use bits, whereas quantum systems use qubits. In classical communication, everything is built from bits. Each bit is either 0 or a 1, so it's very straightforward. But in quantum world, information is carried by qubits, and a qubit can be in a state that is 0, 1, or a superposition of both at the same time. You can think of superposition as the qubit being in multiple states simultaneously until it is measured. This difference is important because it gives quantum communication behaviors that simply don't exist in classical systems. There's a fundamental rule in quantum mechanics called the no cloning theorem. And what does it mean by no cloning theorem? Is a quantum state can only be perfectly copied if you already know exactly what that state is. If you don't know the state, meaning it's part of the secret key, you cannot create an identical copy of it. So, because quantum states don't exist in fixed values the way classical bits do, A qubit might be in a superposition, and the moment you try to measure it to figure out what it is, you change it. So the measurement destroys some or all of the original information. So the no cloning theorem tells us that there is no physical process that can take an unknown quantum state and produce two perfect copies of it. This isn't a limitation of our technology, it's a law of nature. So what does this mean for eavesdropping? It means an attacker cannot quietly copy the qubits being transmitted, because to copy them, they must measure them, and measuring them disturbs the state. That disturbance creates detectable errors in the key. So the no cloning theorem is one of the main reasons quantum key distribution can detect eavesdroppers, whereas classical systems cannot. In classical communication, eavesdropping can be hidden. In quantum communication, eavesdropping becomes detectable. So, if someone taps into a classical communication channel, Alice and Bob have no direct way to know. The attacker can listen quietly and remain invisible. But in quantum communication, is built on the idea of measurement, disturbs the system. So, if an eavesdropper, often which is also called as an eve, tries to measure the qubits, she inevitably changes their state. So when Ellis and Bob later compare parts of the key, they will see strange errors or mismatches that reveal Eve's presence. So instead of silently stealing information, Eve actually leaves fingerprints on the quantum signals. So overall, these differences are what make quantum key distribution so powerful. They give us a communication method where interception is not just difficult; it becomes physically impossible to hide. On this slide, I want to go over a few key quantum principles that are important for understanding how QKD works. The first principle is superposition, which simply means that a qubit can be in a state 0 or in state 1 or in a combination of both at the same time. I have already explained this earlier, so I won't go into detail here. Next is measurement collapse, which is extremely important. So when you measure a qubit, you force it to choose a definite value. Before measurement, it can be in a superposition, but the instant you observe it, it collapses into either 0 or 1 depending on the basis you measure in. And in QKD, this means an eavesdropper cannot look at a qubit without disturbing it. Any attempt to measure will change the state, and these changes show up as errors when Ellis and Bob compare parts of their key. So this is one of the fundamental reasons why eavesdropping is detectable. Another quick principle is the no cloning theorem. It states that you cannot make a perfect copy of an unknown quantum state, as discussed in the previous slide. Finally, the uncertainty principle tells us that certain properties of a quantum particle cannot be known precisely at the same time. For example, in QKD, we use two different polarization bases. So if you measure in the wrong basis, you get the wrong result and you disturb the qubit. That's why an eavesdropper can just guess the correct basis without introducing noticeable errors in the key. So now moving to quantum key distribution. In any secure communication, the first challenge is how to share a secret key safely. So a key is just a random string of bits that both parties use to encrypt and decrypt messages. So if an attacker gets the key, they can read the message no matter how strong the encryption is. And quantum key distribution is a way to share keys securely using the laws of quantum physics rather than relying on mathematical assumptions like RSA and other classical encryption does. So before we move to QKD, we'll discuss about one of the most secure methods for encryption, which is a one-time pad. So in a one-time pad, the key is a string of random bits that is exactly as long as the message. The sender combines the key with the message using a simple operation like XOR. So if the key is truly random and kept secret and used only once, this encryption is provably unbreakable. So the challenge with one-time pad is key distribution. Uh, how do Alice and Bob share this long random key without anyone intercepting it? So in classical communication, sending the key secretly is almost impossible. So this is where quantum key distribution comes in. It allows Alice and Bob to establish a shared secret key securely, even if an eavesdropper listening is listening to the channel. So before I move to BB84 protocol, let me explain what we mean by bases in BB84. Uh, in quantum mechanics, a basis is just a way of measuring a qubit. Think of it like choosing a reference direction. So in BB84, we usually use two polarization bases for photons, which are called rectilinear, horizontal, which is 0 degree, and vertical, which is 90-degree polarization. And the diagonal basis, which is 45 and 135 degree of polarization. So when Alice sends a photon, she randomly chooses which basis to use, rectilinear or diagonal, which bit value to encode in that basis, 0 or 1. So Bob also chooses a random basis to measure each photon, and if his measurement basis matches Alice, he gets the correct bit. If it doesn't, he gets a random result. So this randomness is what makes BB84 secure, and eavesdropper cannot know the basis in advance. So if they measure in the wrong basis, they disturb the qubit and introduce detectable errors. So now let's look at Burnett and Brassard 1984, which is also known as BB84, the first and most famous QKD protocol. So in this protocol, if Alice is sending message to Bob, Alice prepares a series of qubits in random states using two different bases. She sends these qubits to Bob over a quantum channel, and uh, Bob measures the qubits in random bases as well. So after the transmission, Ellis and Bob communicate over a classical channel to compare which bases they used. They keep only the bits where their bases matched. This forms their raw key. So because of measurement collapse, no cloning, and the uncertainty principle, the eavesdropping attempt will disturb the qubits. Ellis and Bob can detect these disturbances by comparing a small portion of the key publicly. So if too many errors are found, they know the channel was compromised and discard the key. This way, BB84 lets Ellis and Bob generate a secret key securely, which they can then use with a one-time pad or other encryption methods to transmit messages safely. Now let's look at an example to see how the BB84 protocol works in practice. So imagine Alice wants to send a key to Bob. The key is the bit string 010100, as shown by the first row of the first table, which she will like later use to encrypt her message. Step one is in Alice preparing her qubits. So the first row shows Alice bits 010100 as shown in the table. So the next row shows the bases Alice chooses to encode each bit, which is Z and X, or which is also called rectilinear and diagonal, respectively. So, for example, for the first bit 0, she uses the Z basis and prepares the qubit ket 0. And for the second bit 1, she uses the X basis and prepares the qubit negative ket, which is 135-degree polarized. So the Ellis sends row shows the actual quantum states he sends over the channel. And step two is when Bob measures the qubits. So Bob does not know Ellis's bases in advance, so he chooses his bases randomly. The row Bob's bases in the second table shows the bases used to measure each qubit. For example, for the first qubit, he chooses the X basis, and for the second X again. So depending on whether his basis matches Alice's or not, the outcome will either match the original bit or be random. And step three is the measuring his results. So the row Bob's measurement shows the quantum states he actually observes. For instance, if his basis matched Alice's basis, he measures the correct state. If his basis was different, the measurement result is random due to the superposition of the qubit in that basis. And finally, the last row shows Bob's classical bits after measurement. uh, we can notice that some bits do not match Alice's original bits. These are the ones where Bob's basis did not match Alice. So after Bob has measured all the qubits, Alice and Bob need to make sure they only keep the bits where they use the same bases. So they do this by publicly discussing which bases they used, but they never reveal the actual bit values. This is the key step that makes BB84 secure. So they compare the chosen bases column by column, and if Alice basis matches the Bob's basis, the that bit is kept. If the bases do not match, that bit is discarded as shown in the table. The discarded bits are colored in black in last row. So this forms the shared secret key, which is 1 1 and 0 0. So what makes BB84 secure is that even if an eavesdropper intercepted the qubits, they wouldn't know the bases LSs used to encode them. Measuring in the wrong basis would disturb the qubits, introducing errors that Alice and Bob can detect by comparing a small subset of the key. So if the error rate is high, they discard the key and start over. And if the error rate is low, the remaining bits form a shared secret key that Eve cannot learn without being noticed. Um, so in short, BB84 security is guaranteed by the laws of quantum physics, not just mathematical assumptions. So far, we have seen that BB84 allows Ellis and Bob to share a secure key using quantum mechanics, but BB84 assumes that both Ellis and Bob are trusted. Now imagine a situation where an eavesdropper already knows the basis Alice is using. In that case, Eve can measure the qubits in the same basis as Alice. Then she can recreate the same qubits and send them to Bob. In this scenario, Eve could intercept the key without introducing detectable errors, breaking the security of BB84. So to address this vulnerability, another protocol called Eckert 1991, also known as E91, was proposed, which uses entangled qubits instead of individually prepared qubits. To understand E91, we need to go back to 1930s when Einstein, Podolsky, and Rosen proposed EPR paradox. They argued that entangled particles must have some local hidden variables that predetermine their outcomes. In other words, they thought that if you measure one particle, it instantaneously affects the other, but there must be some hidden classical information explaining this, or what Einstein used to call a spooky action at a distance. So later, John Bell showed that these local hidden variables could not be tested using what is now called the CH-SH inequality. It's written as the equation shown on the right hand side. So here A and B are two possible measurement set. A and A dash are two possible measurement setting for Alice, and B and B dash are two possible measurement setting for Bob. And E A comma B represents the correlation between Alice and Bob's measurement outcome for a particular combination of settings. So the CH-SH inequality says that if local hidden variables exist, the absolute value of S cannot exceed 2. Quantum mechanics predicts and experiments confirm that entangled qubits can violate this bound, giving S greater than 2. This means that entanglement cannot be explained by any classical local hidden variable theory. So now moving to how E91 protocol functions. So unlike BB84, which uses single photons prepared by Alice, the E91 protocol uses entangled photon pairs. These entangled photons can even be generated by an untrusted source, which makes E91 more robust in certain scenarios. Entangled photons are generated and sent to Alice and Bob. Each pair consists of two photons whose states are correlated no matter how far apart they are. And Alice and Bob measure their photons using randomly chosen bases. Each measurement produces a bit 0 or 1, and they publicly compare the measurement bases, not the results, which just which settings they used. They keep only the bits where their bases matched. These matched bits are then used as the raw key. So now, how do they check if someone tried to eavesdrop? This is where CH-SH Bell inequality comes in. So entangled photons are correlated in a very specific way, and measuring one instantly affects the other. But if an eavesdropper tries to intercept and measure the photons, or measurements disturb the correlations, because the laws of quantum mechanics, there's no way for her to copy or measure the photons perfectly without changing them. Ellis and Bob can detect this by calculating CHSH parameter, as shown by the equation in previous slide, which quantifies the correlations between their measurements. So if no one interfered, the correlations are strong and S can reach up to 2.8, violating the classical limit of 2. But if Eve tried to measure the photons, the correlations are disturbed and S drops below the threshold, and Ellis and Bob know the key is compromised. So they can then discard it and start over. So in simple terms, the entangled photons are like two perfectly synchronized dice. So if no one touches them, they always roll correlated numbers. But if someone tries to peek or tamper with the dice, the correlation is broken, and Ellis and Bob can immediately detect it. So the security of E91 comes from the combination of entanglement, quantum correlations, and CHSH Bell inequality. So even if the photon source is untrusted, any eavesdropping becomes immediately noticeable, making E91 a very powerful protocol for secure quantum key distribution. And now I will show you all the implementation of BB84 and E91 protocol using Qiskit. Just a second. Yeah, so is my screen visible?
Yeah, yes, there was.
Yeah. So I'll start with the BB84 simulation. So first we just import all the required libraries, and this n equal to 50 here means Alice, like we can imagine a scene where Alice is trying to send message to Bob. So here n equal to 50 means Alice will send 50 qubits, and Alice bits randomly generates Alice's key bits 0 or 1, which is like flipping a coin. And Alice bases randomly picks which basis Alice will use to encode each qubit. For example, 0 for Z, which is rectilinear, or 1 for X, which is diagonal. So think of this as Alice preparing 50 photons, each with a random bit and a random polarization basis. Uh, so we can see what are the random bits generated for Alice and the random bases she would be sending the messages through. So for each bit, we create a single quantum circuit. Uh, so if the bit is 1, as shown here, we apply an X gate, which flips the qubit. And if Alice wants to use the X gate, if Alice wants to use the X basis, we apply a Hadamard gate which rotates the qubit into the diagonal basis. So this step prepares the qubit exactly as Alice would send them in a real BB84 experiment. And Bob also randomly chooses a measurement basis for each qubit. And if he chooses the X basis, he applies the Hadamard gate before, like as shown here. If he chooses the X basis, or which is 1, he applies a Hadamard gate before measuring. Then he measures the qubit, which collapses it to 0 or 1. And this simulates what happens when Bob receives the photons over a quantum channel. So here, Ellis and Bob publicly compare which bases they used. Like they compare the bases, not the bits they measured. So they keep only the bits where the bases matched. So this forms the shared raw key. And now let's look at the results of our BB84 simulation. So in our example, we can see that out of 50 bits, 25 25 positions had matching bases, which can be seen here, like indices with same basis. So in these bases, they use the in these indices, they use the same basis to measure the qubit, and L is to send the qubit. So if an eavesdropper try to intercept the qubits, he wouldn't know which basis to measure. Um Measuring in the wrong basis would disturb the qubits, creating errors that Ellis and Bob could detect when comparing a small subset of their key. So this process ensures that Ellis and Bob can securely share a secret key, and any attempt at eavesdropping would be immediately noticed. So to calculate the error here, we are comparing all the bits Ellis and Bob. So we can see that no bits are different, which gives the error as 0%. We can put some threshold, like if the error rate is more than 20%, there's an eavesdropper, and both Ellis and Bob can restart the process to generate another key. So in the real simulation, only the subset of keys measured are compared, but here I am comparing like all the 25 keys, matching keys. So this example was without the presence of an eavesdropper in between. If there was an eavesdropper, the Eve would have measured the qubits in between and send the new qubits to Bob, which would cause the error to increase. So the implementation with eavesdropper has been given as a task in the task sheet for today. So you all can try to implement BB84 with the presence of eavesdropper and see how the error rate behaves. So now moving to the implementation of E91. Does my screen changed? Yes. So for E91 simulation, we chose N as like 100 entangled photon pairs, and Alice and Bob each randomly choose one of the two measurement angles for the photon detectors. So Alice can choose 0, which is also A1, or pi by 4, which is A2, and Bob angles can be pi by 8 or pi by 3 pi by 8, which is B1 and B2. So these angles correspond to the measurement settings used to test Bell's inequality, and the function create entangled pair builds a quantum circuit for an entangled pair. So uh, first we create a quantum circuit with two qubits and two classical bits, then put the qubit 1 in superposition, which is the Ellis qubit. Then again we add in like we add the C0 gate, which entangles Ellis qubit with Bob's qubit, and we apply QC dot RY, which rotates Ellis qubit according to our chosen measurement angle. And again, we add QC Y gate to the Bob's qubit according to his angle. And finally, both qubits are measured. And this simulates the entanglement experiment. And we are using AR simulator to run our quantum circuits on the classical computer. So the measurement outcomes for Ellis and Bob would be like 0 or 1, and the measurement choices, which angle they chose, would be stored in these lists. So for each pair, Ellis and Bob randomly choose one of their two measurement angles, which is shown by these two lines, and store their choices, like what angle they chose, and they create they create a circuit for the entangled pair with the chosen angles and run the circuit in the simulator and extract the measurement result. So 0 or 1 for each photon, and store the results in this list for later correlation analysis. So the correlation function calculates the correlation between Ellis and Bob's measurement for a particular pair of angles. First, it finds the indices where Ellis and Bob use the specific angle combination and extract the corresponding measurement results. And it maps, like it converts 0 to +1 and 1 to -1, because correlations are defined as like plus minus values in Bell's inequality. And finally, they multiply Ellis and Bob's values for each trial and take the average. So result would be a number between -1 and +1, indicating how strongly correlated their measurements are. So +1 would represent perfectly correlated, and -1 would represent perfectly anti-correlated, and 0 would represent uncorrelated. So This is nothing but the CHSH inequality formula. Here we calculate correlations for all four combinations of Ellis and Bob's angles, then compute S to check Bell's inequality. So if S is greater than 2, the Bell inequality is violated, which cannot be explained by classical physics. So this confirms that photons are entangled and no one has interfered, and Ellis and Bob's key is secure. But if S value would be less or equal to 2, the correlations are weak that could indicate eavesdropping or noise in the quantum channel, so they will discard the key and start again. So this was also the example without the eavesdropper, so we can implement this as a task with the eavesdropper to see and compare the value of S. So this is all from my side, and I think now Swati will take over from here.
Thank you, Devashish and Shanika. Just give me one sec. I'll just share my screen. Can you see my screen?
Yeah.
Yeah, great. So I'll just quickly sum up a little bit of what Devashish said and I'll move further. So, up until the 70s, people have had a way to encryption, but they had to meet up in person and then share a common key, which they would use to further encrypt and decrypt their messages. This works only until the key is kept secret. If anyone else gets their hands on that key, then obviously they also can view the content, which Devashish told us like about the eavesdroppers. So this system until then was called like symmetric key system. So then further on came a system called RSA, which we use till today. RSA works something like messages are sent by multiplying very big prime numbers. We are talking about hundreds of digits of prime numbers. They are multiplied and then created as a big, much bigger composite numbers. And then to read these messages that two people share, people should be able to figure out with what two prime factors that the big number was made. Only then they could decrypt it and the message would be violated. So trying to figure that out will take our today's computers like millions of years. That is why we have a strong encryption to date. Even though we don't have, we don't yet have large scale quantum computers which can break the RSA today, we already see like devastating cyber attacks that are happening with classical technology alone. Some terrible attacks that we have over the years are related to breach of personal information, client data, attack on power grids, nuclear centrifuge, ransoms, and etc. To perform any of these attacks, hackers need data. So, quantum computers, if they are known to crack this uh, encryption that we have in much lesser time because of their performance. So we need to prepare for the day. More importantly, there could be people who can get the hands on some crucial data and store it with them to decrypt it when the quantum computers are available, uh, which Devashish mentioned, like it could collapse instantly. So this is what is called store now, decrypt later. That means they have the data now, and when they have resources, they will be able to crash the whole systems down. So when it comes to algorithms, we have Peter Shaw's algorithm, which already proves that they could solve this integer factorization problems. And then we have Grover's algorithm that speeds up the brute force and hash functions and all. So for all of this, there is one common factor. That is, this data moves through a network. That means before, sorry, was there a glitch? Okay.
No, it's
Okay, sorry. So Sorry, I lost track. So yeah, the data will be moving through a network. That means before or during or after an attack, the network traffic and the system's behavior start to look a little bit different. So the changes or abnormalities in this behavior over the network is anomalies. And we will explore a way to detect them today. These are detected by training a model on huge amount of data and then testing on the model on some unseen data, like any other machine learning algorithms work. And once we know that the model is performing well, we deploy it onto our network. And whenever it sees some abnormalities, it alerts. It alerts, and then you can perform action. This is how it works. So, some kind of abnormal behavior or out of the expected behavior is an anomaly. So, when it comes to where this anomaly detection works, we could do it in common domains like fraud detections in healthcare, in networks, in sensors, in automobiles, everywhere. So when it comes to what type of anomaly detections are there, first is a point anomaly. This could be in a spike of information or something like that. For example, it, if you are a person who walks like 5,000 to 10K in a day, steps in a day, and then there is this one random day where it shows like 50K or something like that. You ran a marathon or something, but the system is going to show it as an anomaly so that as a human, you can check it and rectify it, like you can classify or not. And then comes contextual anomalies. This is an anomaly usually happening with your bank transactions, where there is a random expense out of the pattern that is observed in your transactions. And then there are collective anomalies, which happens when you do multiple transactions in time. Come holiday season, there are good sales going on, and this could be popping up everywhere. And temporal anomalies, this is when you are bombarded with messages or something, and your phone sends you an alert, or any app that you use sends you an alert. It's something like that. And spatial anomalies are which happens usually in our GPS systems, where sometimes if you're traveling through a car, it randomly shows up that you're walking over the water or something like that. But when you refresh, it's fine sometimes. And then comes multivariant anomalies where multiple features matter, like suddenly there's a bank transaction somewhere far away from your country at a very odd timing, at a very suspicious merchant, and then your credit card sends you an alert. That's what these are. And then, okay, going further, how to detect these anomalies. Okay, first, Uh, sorry, can I request everyone to be on mute until the Q&A, please? Thank you. Okay. When we come to detecting anomalies, first we need to get our data straight, especially while working with quantum computers. Preparation of your data is very important. So, as any other preparation, like for common classical machine learning, you handle all your missing values, remove if there are any errors, and you perform all the feature engineering required. And then when you come to modeling approaches, there are different ways you can do. These are mostly related to your machine learning things, which you'll be seeing in day three. Um, so I will just quickly show you. Uh, don't worry about the right side code. I'll be explaining it directly through the code. That will be easy.
I think
Yeah.
Swati, yeah, okay,
Can you see the screen?
yeah, yeah.
Yeah, okay. So here, just for demonstration, I'm randomly creating a dummy data here, just a toy data set. This is our initial data set, which has about 10 columns with it's a network data set, okay? It has time, source and destination IP addresses, ports, protocols, and flags, what duration was, and labels and everything. So this is just a code that I use to just generate random data. You don't have to be worried about it. And let's go through the data set. This data set has 240 records and it has 195 normal, very fine working records. And then it has 45 anomalies. And then label goes to what different types of anomalies are here. We have 4 different types. And then comes to the first point that we were discussing, handling missing data. That is, you just find what missing values are there. These are the missing values related to different rows. And then we choose to drop those values right now. And then in the next part, our label, that is our target column, that is if it's an attack or not, has different types of attacks. So we are going to perform label encoding or categorical encoding over there, which will give them labels. Like if there are 4 different attacks, it's going to give 0, 1, 2, 3, 4 instead of the whole name, because we need to convert everything into numbers for quantum computers to be understanding properly. And then we are going to split the data set, whatever we have, into 80-10 proportions. So 20% will be on the training set. And then we perform standardization. And then when we come to actual quantum code, here you can see that, sorry, here you can see that we're using feature maps to encode the data. We are using VV feature map. And then we are putting a sampler. Sampler is an object that actually runs on the quantum circuits, and it returns the measurement values that you've seen until now. And then we have a compute and compute. Compute and compute is a specific method that is used to calculate the fidelity between 2 quantum states. Like in the previous slides that you've seen, they are 0001 and all that. So it is used to measure how similar those 2 qubits are. And then, uh, and then when we use the quantum fidelity kernel, it is basically that you're telling the system that I want to compute a similarity between my data points using the fidelity of the quantum states, something like that. So to do this, the kernel needs a way to calculate that fidelity. So compute and compute is one specific way that tells the quantum kernel to perform this calculation using a quantum computer or a simulator. And then you train it on QSVC. It's quantum support vector classifier. And then you predict, and roughly you have the accuracy scores here. So it's telling that, okay, it is 80% show that these the distributions that there are these anomalies here, and 38 normal. You might be worried like we had a lots of rows. What about this? This is only on testing data. That is 20% of our original data. And one more thing that you would be wondering here, all through until now, yesterday and today, you were seeing all about quantum circuits, simulators, and stuff. Where are they? They are running without that, without declaring any of that. So even if you don't declare, Qiskit has its own way to have a default running through. So what is it running on? If you want to find out, we have encoded our data on the feature maps. So we try to print it. And now you can see that there are 10 qubits from 0 to 9, and it's just 10 different qubits. Why specifically 10? Because in our initial data set, if you can see, sorry, There are 11 columns, and we drop the last column because it's a target column. So 10 different rows, 10 different columns is 10 different qubits here, and they're completely empty. Empty in the sense like they're not manipulated with any gates yet. So if you are just using normal code, this is how it works. But if you want to create a custom circuit, you can just apply any Hadamard gate, or CNOT gate, or anything, and you can print your circuits. And you can also just print your circuits, or you can draw, like you saw in yesterday's needs workshop, and it will create a better visual for you. So this is how we can do anomaly detection. And Shanika, would you like to take over for the task sheet?
I think you can go ahead if you,
Okay,
yeah, it's good.
one sec. Let me bring it up. Okay, okay. Hmm, can you see my screen?
Yeah.
Yeah, yeah. So for day two's task sheet, we have three different tasks here. And the first task is split into A and B. So first will be related to teleportation. And we have pretty much everything uh, clearly laid out step by step. And oh, sorry. Oh, what's wrong? Yeah, sorry for that. And then B will be the super dense coding, and C will be regarding the protocols, and then D is the anomaly detection part. Here, specifically related to this task that we just discussed, it's pretty much laid out the same way that I've already explained. It's just that you will be using a specific data set that you can download open source online. And And please make sure that the all the tasks are in IPYNB format, even if you use Visual Studio Code or Google Colab or Jupyter Notebook or anything, because we will be running all your code and testing if everything's working fine or not. And related to few queries that we've received, um, everyone has to pass all the tasks to receive a certificate from us at the end of this course. And you would have received a day one email where we had all the links and the resources for day one. We will be sending out that again because there's a problem with the recording link. We will sort it out and get back to you as soon as we can. And we will also once again just getting it out there that we are aware of all the problems that we are facing with the discussion forum, and we will be getting that sorted and getting back to you as soon as we can. That's it from my side. Does anyone have any questions for us?
Swati, I need to just I need to clear one thing. We just
Yeah.
send the again mail for the discussion form, and you students needs to just join that, and they can ask and discuss there directly. Now it's working. So I just push the email. Maybe you will get the email slowly for everyone. So
Oh, that's great.
yep, yep.
Yeah,
Thank
that's
you.
great. Yeah.
Okay, this is
Any,
done for the today. That's I think this is the time for you to clear up your any questions. Obviously, you will have any more questions or confusions. So You can ask questions. We are happy to help you. If anyone has questions. Okay, you can go through the, it seems like no questions, but obviously you will have once you go through this again and once you go through the task sheets that we will be here for you. And once you go for the task sets and when you go through, you can feel like, okay, I have this question. And even you may think it's a silly questions, but not silly questions here. They're like, that every part that if everyone has a different knowledge capacities and different backgrounds. So you can ask anything related to the quantum, these theories yesterday and here today. Yeah, okay. Yeah, Benjamin, I see that you have a question.
Yeah, this might be directed to Swati. How suitable
Okay.
does she think anomaly detection is in time series forecasting or time series data sets?
Swati, it's for you to, yeah.
Sorry, I didn't get that. Can you just repeat it?
Sure. Um how related do you think anomaly detection is for time series data? So that you were using like a static data set there, but do you think it's related at all to time series data?
It is related. There are a lot of good research going out there, and it is still like upcoming.
Yeah.
Yeah, we could still use whatever is existing, and there are new algorithms coming up every day. So just keeping up with research, that's it.
Okay, cool. Thank you.
Yeah,
Uh,
thank you,
yeah,
Swati.
thank you. I have another thing to discuss. To let everyone know about the submission. You can submit your task. It's not compulsory to submit on the next day or the before the next session, but you can take your time. But we are expecting you guys to submit all the tasks, as well as we will give you one capstone project before 26th of November. Basically, what is that? We will give you seven day after all this session will when it these session is finished. So basically, it's after 20, sorry, after 19th, you will have 7 days to submit everything, which has the day one task, two, three, and four, and as well as the capstone project. So yeah, I think these are the main queries which we are getting, and I already discussed told you about the discussion forum now. It's active, so you guys can join and we can start this. Like you can share whatever problems you are having, and there is another problem. I think uh, the people from Iraq might be getting they are not able to sign in on IBM platform. It what we think uh, it is a geographical issue. Maybe IBM does not allow Iraq as a location to sign in. So I'm trying to find some other ways how you guys can log in there, but I still need time for that. So I think this is from my side also, and we will meet you tomorrow with quantum machine learning, and that's
Excuse me,
what.
sir.
Yeah, yeah.
Sir, may I know how to join in a discussion forum, please?
You will get email. You already, I think, I just 5 to 10 minutes earlier I sent the mail to everyone.
Oh,
So
okay,
yeah,
okay.
so you have a link there, and just if you click, you will automatically add it to Teams
Yes,
channel.
yes. Yeah,
Yeah,
yeah. It's came.
yeah,
It's came. Thank you.
yeah, yeah. Yeah. Yeah, Rasul.
Yes, sir, it's came.
Okay. Thank you.
Okay.
Yeah.
Excuse me, I
Yeah.
need to say about the mail of discussion. It is not working. I just access to it and not working. I don't know.
The email which I send you now.
Yes, after a few minutes
Okay.
before. Sorry.
Okay. Maybe still because we are adding you one by one, everyone to the discussion forum. So maybe your name is and the I think at very end of the list, so you will get that. So it
So
is
there is,
yeah.
I
sir,
don't know, but
excuse me,
he
sir.
it is need for code verification on mail. When enter on it, it is not
Yeah.
working. It is appear like error.
Here then because we just checked with outside our own system, it is working for us. So let's wait for you for your name to be added through our own system. So if it is not working, please let me know through the email. I will try to solve that thing.
Okay,
Is it
thank
working
you.
for
Yeah,
anyone else so that you can confirm?
yeah.
I'm getting the same error as Rusal.
Okay.
It
I
says,
the same.
when I click the link, it says we can't take you to that chat because it's in a chat you're not in.
Okay. Okay, I will see again why it is like this
Uh,
because earlier,
Navneet, you
yeah,
said that you're adding one by one, right? Can you just
e-
ask the
no,
first or early
I
people
think
to just confirm?
I in- I think Dr. Shiva will add because
Okay.
he has
Oh,
that
okay.
thing, but yeah, but you will get because we just checked with other person, they are able to get it. So let's wait for a couple of like maybe some time and it will be there. We are trying to solve that issue because I know like a lot of questions are there, but yeah,
Okay, sir. Thank you.
thank you.
Okay, thank you, Navneet. And I think now you can try to work on this task sheet. So, and while you are working on in the remaining time, that if you have any questions that you can ask and clarify whatever the things that you need to clarify regarding the task sheet as well. So let me share it's the um, yeah, this is the task sheet that all of these are related to that what we have already discussed today. So yeah, you can start.
if no one is having any question at this moment, maybe we can just end our session for today. And once the discussion forum is up and running, you guys can ask questions there. Otherwise, we'll be back like again tomorrow, and you guys can ask your questions then.
Uh, can anyone confirm that now the link is working or not? Because I was able to log in with outside from other account also, but I'm still not sure. Let me.
Same
Actually,
error
no,
for
sir.
me.
Yeah,
Same error
just
for me
one
now.
minute. Yeah,
Actually,
yeah.
no, sir.
I will. Yeah, I will add one of you so that we can confirm that. Uh, okay, Benjamin. I will add your email.
Can you make sure you
Uh,
use the Deacon email? Because I think yesterday or the day before when I signed up, I ended up using two emails because I wasn't sure. But do
okay,
the one that ends
okay,
at Deacon. Yeah.
okay. But Deacon, any other person who is not from Deacon, because we need someone with because Deacon person can be an advantage.
Sir, actually,
Yeah.
sir, actually, I also can't like log in that comments. Like that is a chat.
Okay, okay, okay. Let me add you. Yeah, add your email. Mm, Uh, can you check now? If,
Yes, sir. Yes, sir. I'm checking. I'm checking.
yep, please.
Sir, could you add mine also?
Yep, sure. Uh, it's-
Sir, actually, now also the same thing is showing. I can't join there.
bec- because I added you, but I can I how I can tell you. I added your name, but still, someone Salma is uh, and
Yeah, I just added my one friend from there. Enter his name and added.
yeah. So these people can join. Okay, that means this
Yeah,
link is
now I can.
working. Yeah. Okay, then that's good. So so can you some of other can check.
Excuse me,
Yep, yep. It
it is affected if I open from iPad or from laptop.
usually does not. uh, I don't know why it is like this because from my own testing and I have done with couple of other people, but it is going through. Can you use the link which I send you and login in Google, sorry, in Teams in with any ID, whichever ID you have, basically Microsoft ID, you might be able
Okay,
to get it. Yeah, I will.
I will try. Thank you.
Yeah, yeah. And other thing is, because you guys are uh, joining this as a guest, so maybe it is the reason why you are not able to join. If you already provide us email, so maybe for example, if someone is joined with their email address, maybe they are able to easily join that chat. So if you do not have a, a Microsoft account, you 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 might not be able to use this. Or you can try with that. You will either you join you log in through with your email ID and create an account using same email ID which you have registered in Microsoft Teams.
Sir, actually, I have the Microsoft account with my
Yeah,
personal email
okay.
ID,
But
but
still it is not.
I registered
Yeah,
in this way.
okay.
Actually, it is not working, sir.
But I think I can see your name that you are already in the, yeah, in the system.
Okay, sir. Let me check. Let me check, sir.
The name is the ATIS 2025 Discussion Forum Help Hub. The conversation.
Hello, sir. After clicking
Yeah,
your link from,
yeah,
I'm trying to do this from directly from the team app as well as from
okay,
the website. So it's
yeah.
showing me the same interface that click here for the new chat, send instant message, share file, and more over the chat. And another is skip the calendar. This kind of the front interface basically.
Okay, so uh, can't see. Uh, we will try to add everyone. Like
I think you need
some.
you people need to create a Microsoft Teams login, right? So make sure that
Yeah. Yes, yes. I will share my screen to show you like what I am able to see so that you will see. Yep.
yeah, I see better.
Yeah. This one. Now, are you able to see my screen?
Yeah, yeah.
And you, yep. So this is the name of that the help up session. So you just go here and you guys can have that because how I will because I have the link which I have shared with you guys. You just come here and you can see this interface, I think, because we already tested with these people and they showed that they tell us that they can message here. So I'm not able to get it why it is not going through. If let me, yeah, Amir.
Hi, thank you for your precious
Yeah,
information. And
yeah,
I want to ask you, I just make a Microsoft account and
yeah,
signed in and joined the email you sent me, but the
yeah.
discussion form is empty in my screen. Can you please add my email manually?
Uh, can you? I think I'm sharing screen, so I can't add you directly. Yeah,
Um,
let me. Yeah,
I think
yeah.
if someone it's
Can you can you?
happy to share their screen, then you can
Yeah, that's also nice. If
yeah,
someone else can try because I have everything with even Deacon systems and even every login. So
yeah.
if it is better, yeah. Anyone who is willing to volunteer for this, we are happy to assist.
If anyone of you having this problem can share your screen, if no problem there, so then
Yeah.
Navneet can just look in that what happened there. Because you already have all setups in our systems, then we cannot exactly understand what your side happened, right?
Okay, sir, no problem. I'm
Yeah,
sharing my
yeah,
screen.
yeah. Sure, sure, sure. Please.
Sir, now I able to join that chat, sir.
Yeah, maybe. Yeah.
This is your
Let's
mail,
let's. Yeah, 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 yeah,
and I'm clicking over it.
yeah. Can you go to the chat? Just chat on the Teams app, left side chat. The icon says there is nothing, or
No,
just click on Teams. Then just below. Yeah. There is some problem with the with your system. That's why you're
yeah,
not getting. Can you log in and log it out?
sir,
Yeah,
I can do it from here, like
yeah,
what I was doing before.
yeah. Please.
If you're doing it through an app, can you make sure that it is up to date?
Can you go through conversations or somewhere? Not channel. It is not. Hmm.
So nothing is showing.
Yeah, I can see that. Can you share your email address so that if I can try to
Yes,
to
sir.
to yeah, please.
So my Outlook
Yeah.
email or what email
Whichever
I did?
whichever you prefer, whichever you prefer right now, because we need to sort this. So I just need to see.
Okay, so this is my
Let me.
Muskan Sinha 2004 @ outlook.com.
Okay, Muskan. Uh, Muskan. Yeah,
Yes.
Muskan.
Yes, sir. Now I'm able to see this.
I mm,
Done,
yeah,
sir.
yeah. I think Salma somehow help help us to get it you through. So that means someone needs to individually. Okay. So you can
May
see
I
now.
stop sharing?
Yeah, sure. So thank you for helping us. Yep, thanks. So what we will do is we will start uh, manually putting you guys in the discussion form. So maybe you guys need to at least 1 or 1.5 hour. We'll sit and I will manually do this. So I think other than this, everything is sorted. Amir, you want to ask anything?
Yes, please. Can I share my
Yeah.
screen?
Yeah, please,
Okay,
please.
just a minute. Is my screen showing now?
Yep.
This is what I get. I think I am joining through the website, not the app, but I don't get the discussion form here. What should I enter
Yeah.
here?
You can't enter anything here because we have to put your email address. So
Uh,
because you are even this workshop session you are uh, joined as a guest. So otherwise I can just copy your email and put it here.
okay. Okay, I
Uh,
tried to sign through the email, or my institutional email, but it says I can't join to Microsoft using an institutional email. So I have to go
okay.
through my personal email. I will send you just a
Okay.
minute. I will send you the
Okay.
email. Can you open me?
Okay. Okay.
Just a minute.
Excuse me, it is the same for me, this screen. There was no email accepted to send.
Sorry.
This screen is same to appear to me when
Okay.
you need. need email to send anything, it is not accepted for the email of Quantum Lab.
Okay. Uh, I'm not sure also because some of you guys can join, some can't. But well, let me see. Mm. Okay,
This is my email.
okay.
Can you
Just
please
keep
guide
it
me?
there. Yeah. Just keep it there. I will just type it.
Okay, thank you.
Yeah. Can you check now?
Okay, where should I go? Go to chat or
Yeah, chat or Teams or conversation, wherever. Just reload the thing.
okay, so let me reload the page. Yes, I think I get the request. Okay,
Yeah.
okay, I should accept it now.
Okay. Oh,
Okay,
anyone can. Any. Okay.
thank you
I
so
don't.
much.
Yeah. So I think. Uh. Okay. Yeah. Kimmy. Now you can come.
Hello, just same my issue I am also facing. Just need to add my email ID in the chat.
Okay. Let me add everyone. But the issue is, I can only add those email addresses which you guys have shared with me. Basically, which you guys have
My
registered from.
Microsoft, actually I
Yeah.
have the Microsoft account with a different email ID, so maybe I
Okay.
you need to add that email ID.
Okay, but I think it should work, but I not sure because I have a different email address. I just log in, I just click it with that, and it logged in me. It logged in because this Navneet Singh oh sorry, I will share my screen. I will let you know like what I'm trying to say.
Okay.
Yeah. If you guys can see, uh, this Navneet Singh, which is it. This is my external. So I just click it here, and on my Microsoft account I can just add it in here. But I don't know why you guys are not able to do that. Uh, Let me then if you guys can wait for at least like 1.5 hour or two, I will add you manually. And if you guys are not added by within next 2 hours, just send me your email which has the uh I can say the G or Microsoft account. Yeah. So so it might be helpful for me. So otherwise this session can go very long if I start it. Is it okay if you guys can wait for next 2 hours and I will add everyone? And if you see in next 2 hours you are not added in ATIS discussion forum help hub group in Teams, please email your Microsoft account or Microsoft Teams account email address. I will add. This works.
Okay, Okay, sure.
Sure.
Yes, yes.
Okay. Okay. Thank you. Any other?
Okay, it's now
Yeah.
seems like yeah.
Yes. Yep. Thank
Uh, now we can wind up our session for today. Thank you for all for joining today. I hope you got the full of informative details about the quantum things today related to cryptography and communication. So I hope you enjoyed the session and gain full of knowledge and hope you will be able to gain more and more knowledge later on coming up days. We have um, instrumental lots of resources for you to share. And okay, let me stop the recording and let's find up this session for today. And yeah, stop recording. Okay, good day for all and